So now let's talk about independent samples t-test. How do we know when we use this type of analysis? Well, again, with all t-tests, when we want to compare two group means, okay, that we always know two group means, going to be a t-test. How do we know then independent versus single sample? Well, in this case, we don't know what mu is. So we don't have a single sample that we can compare to a population sample. We're going to have to actually collect two different groups. Okay, we could talk about experimental versus control. Talk about, this example, boys versus girls, whatever it may be. We're actually looking at two different groups. And then finally, we know we need to use an independent samples t-test when the observations themselves or the scores we're looking at are independent of each other. In other words, there's no reason to suspect that one participant's score is related to another participant's scores. Where you would see sort of violations of this, let's say if it was the same person taking multiple tests. Well, if they're taking a test more than once and those are the two scores you're looking at, you would expect test 1 to be related to test 2 because it's the same individual. But for independent, there's no expectation that these scores are related. So independent sample t-test. And let's walk through this using this example. So a teacher wants to know who has higher self-esteem, boys or girls. Takes a convenient sample from his class, and gives the students, 7 boys, 8 girls, a self-esteem test that ranges from 0, which is on the low, to 40, which is a high score. The teacher hypothesizes that it's going to be girls who have a higher self-esteem. Question we want to know is he correct? Is his hypothesis accurate? Here are the data. Kind of look at it and begin to kind of guess that he's probably not correct, but we need to analyze this anyway to see if it is in fact the case. So get out your 7 steps for NHST and let's walk through them. So step 1, let's write out our hypothesis. The null hypothesis first, the the self-esteem for boys is equal to that of girls. No effect, no difference between the two. That's the null. The other option is our hypothesis that boys are going to have a lower self-esteem score than girls. The little asterisk there is because that's the one we're predicting. Then we also have the other end where maybe it's boys have an actually higher self-esteem than girls. Okay, so there's our 3 hypotheses. Then we go on to step 2, which in this case we're looking at a t-test, specifically an independent samples t-test. So that is the analysis we're going to run. Let's go on to step 3. We want to figure out what our critical values are. Well, in order to do this, we need to know what our alpha is. We know it's 0.05. We also, as we talked about with a single sample t, need to calculate our degrees of freedom. For an independent sample t-test, you take the size of group 1 plus the size of group 2 and you subtract 2. In this case, we had 7 boys and 8 girls for a total of 15 participants. Subtract 2 from that, and now we get 13. So now we know we have an alpha of 0.05 and a degrees of freedom are equal to 13. So we can look at our t-table again. In this case, we still know we're looking at a two-tailed test. We're still looking at an alpha of 0.05. So follow the degrees of freedom down the left-hand column to 13. Move to the right 1 row or 1 column, and we find that our t critical is plus or minus 2.16. So we're looking for these t values that are 2.16 or weirder or further out. Okay? Go on to step 4. We're going to actually run the analysis. And here is our SPSS output again. As you will note, our descriptive statistics are in this top box, as is the standard format for SPSS. So we can look at that first line. We see self-esteem. That's our variable that we're interested in, our dependent variable. And then we also see gender, the males. We see that there is 7 males, 8 females. You move to the mean column, and we can see the mean score for males. So the males had a self-esteem score on average of 32.57. The female mean score was 21.13. and we can see their related standard deviations in the next column. So their standard deviations, about the same. One was 5.28, one was 5.74. Okay, so those are our basic descriptive statistics for this sample. Let's drop down now to the second box where we can look at the actual analysis. You will notice the heading there, it says independent samples t-test, and just below that to the left is this new box that says Levene's test for equality of variances. This is very important. Below that you will see an F and a significance value. These two columns are telling us whether or not these two groups, male and female, have roughly equivalent variance, or that their scores roughly reflect each other in equivalent distance. So I want you to think about this. Let's imagine we had given the boys a self-esteem score and every boy had a self-esteem of 50. And then we had given the self-esteem score to the girls, and the girls ranged from 5 to 40, whatever it may be, okay? In this case, we would say that the boys didn't have the same type of range as the girls. The boys had one score. The girls had multiple scores. What we're not saying is that they have to have the exact same scores, but the range of scores should be the same. So if the boys range 5 different scores, we would expect the girls to range roughly 5 different scores as well. They may be higher or lower, but they should cover the same sort of range. If we violate that assumption, then we have to make an adjustment for a type 1 error inflation. Okay, this is one of those assumptions for the t-test that we don't want to violate. So if we go back to this significance value under the heading Levene's test for equality of variance, we find that the significance value is 0.98. Okay, so P equals 0.98. Is this statistically significant? Is it higher or lower than 0.05? It is greater than 0.05. So we know this is not significant. In this case, for this test, it is great. We don't want this to be significant. What this means then is the null regarding their variances is true. There is no difference between the variances. This is a good thing. So when we find that this Levene's test is not significant, it tells us then that we are to use the top line or this top row of numbers for our analysis. If this had been statistically significant, it would tell us we need to make some type of an adjustment for type 1 error. We would use the second row or the second line of numbers. But again, 0.98 is not significant. Let's use the top row. So if we follow that top row across to the t column, we find that the t value for this particular sample is what? Our t equals, what's the value? 3.99. Okay, so this is our t observed, is 3.99. Follow on over, we know that our degrees of freedom are 13, which we calculated that just a little bit ago. And now we see this significance two-tailed, which we know is our p observed value. In this case, what is our p value? It is 0.002. Okay, that's pretty tiny p value, right? So let's just stop here for a moment. We've got our graph drawn out here, roughly. We've got a p that's equal to 0.002. We know now that is way less than 0.05, so it's going to be somewhere out here, right? Is this in the rejection region? Yes, it is in the rejection region. So we can conclude what? That we reject the null. There is a statistically significant difference between the boys' score and the girls' score. Okay, so let's go on then to step 5. We want to make our conclusions. Okay, as we just said, we know this is statistically significant, but here's the tricky part. Okay, the hypothesis by the teacher was that girls would have a higher score. What did we actually find? If you go back and look at the means for males and females, now we can look at those means and make a conclusion. Wow, there was a difference. We found it was statistically significant, but it turns out it wasn't what the researcher thought. It was actually the opposite. It turns out boys with a mean of 32.57 are significantly higher than girls with a mean score of 21.13. So how would we write this up? This is our basic jargon, and there are multiple ways you can word this. You can word it however makes sense to you as long as it's accurate, but this is the type of phrasing we're looking for. Contrary to what was expected, boys, and then include their information, had significantly higher self-esteem score than girls, include their information, and then according to APA, I want you to write out the statistical value. In this case, it's a T with 13 degrees of freedom, and the T value is 3.99, and then the P value is equal to 0.002. Okay, so that is our conclusion. That's what we found. Now we want to go on and we want to calculate our effect sizes. So let's go over here. I'm going to move out of the way. We're going to calculate our effect sizes here. And what we find is this is a new effect size. We're no longer going to use Cohen's d for independent samples t-test. We actually have this little, looks like an N. It's called eta, and it's eta squared. And so the way we calculate this is by taking our t observed squared. So in this case, our t observed is 3.99. We're going to square that, and we're going to put that over 3.99 squared plus our degrees of freedom. What were our degrees of freedom in this study? You can look at your table here or go back to what we calculated before. It is 13. Okay, so if you get your calculator out, we can take 3.99 squared, and we're going to divide that by 3.99 squared plus 13, and that's going to equal 0.55. Okay. So eta squared equals 0.55. I've provided you the basic conventions here of what we determine small, medium, and large effect size. Small 0.01, large 0.06, or medium 0.06, and large is 0.14. Well, this is a lot larger than 0.14, so we would conclude that this is a large effect size. Okay, so eta squared is a large effect size. The last thing we want to do then, step 7, is calculate our confidence intervals. But again, fortunately for us, SPSS does this. All we've got to do is find those values, and again, it's located in the right-hand column of the output of the second box. Again, we're looking at the top line, so our lower bound value is 5.26 rounded to 2 decimal places, and our upper bound value is 17.64, which is rounded to 2 decimal places as well. And so that basically tells us that we are 95% confident that our true population value lies somewhere or is captured between the values of 5.26 and 17.64. Now, you as a researcher would have to conclude whether or not you think that is narrow, whether you think that's sort of middling, or whether you think that's sort of wide. If we talk about the scale, it was 0, I think, to 40. You know, you're talking almost a 10 to 12 point range. That's almost 25% of the scale itself. I would call this probably a wide confidence interval. You can certainly debate it, but I do want you to sort of get used to or being a little more comfortable making a decision, because when it's your research and you're the expert, you're going to have to tell me whether this is meaningful or not. Okay, again, I need statistically significant, I need effect size, and I need confidence intervals so I feel good about your research and your conclusion.